In this video, we will be looking at two different periodic trends. We'll first look at the size trend, sometimes known as radius, and then after that look at the trend for ionization energy. We want to start first with the size trend. And when we look at the periodic table, we're going to see two different trends that happen. One happening vertically and the other happening horizontally. I want to start with the vertical trend because that one's a little bit easier to understand. When we go vertically, size is going to increase as you move down the periodic table. And that's kind of what we would guess would happen as we move down the periodic table, that atoms would get larger and larger. But we still want to go through and actually explain why that's actually happening. The reason that is happening is as we go down the periodic table, we're getting larger and larger energy levels. Remember, that N value is how far those electrons are away from the nucleus. And the size is going to be based upon how far are those farthest electrons away. So let's look at an example. Potassium ends up being bigger than sodium. We can use our electron configurations to take a look at this. So if we write out the electron configuration for sodium, we'd have 1s2, 2s2, 2p6, 3s1. If we do the same thing for potassium, we'd be looking at 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The electrons we care most about are those that are farthest away from the nucleus. So if I circle the ones that are farthest away from the nucleus, in sodium that would be in a 3s orbital. If I circle the one for potassium, this is in a 4s orbital. If you just think about what that N value is, that N value is telling you the size of the orbital. Down below, if we think about a comparison of a 3s orbital versus a 4s orbital, a 4s orbital is going to be naturally larger. So that is why potassium ends up being bigger than sodium. Those farthest out electrons are in higher energy levels, so they're going to be much farther away from the nucleus. So the vertical trend matches our expectations. The horizontal trend is going to work a little bit differently. Horizontally, size is going to decrease as you move to the right across the periodic table. Now this isn't what we would necessarily expect. It's a little counterintuitive. We would kind of expect if we would first look at the periodic table, as we go to the right, we would kind of expect things to get bigger. But what's actually happening is things are getting smaller. So let's actually look at an example. Carbon is larger than fluorine. So this isn't something we would automatically expect right from the beginning. We'd kind of guess before reading through this and thinking about this, we would kind of think maybe fluorine would be larger than carbon. But it's actually the other way around. So for this, just like for the vertical trend, we need to have a little explanation going on for what's happening with this. So for this, we're going to start out with the electron configurations again. For carbon, 1s2, 2s2, 2p2. Fluorine, 1s2, 2s2, 2p5. If I circle those outermost electrons, again, here I'd be in a 2p orbital in each case. Notice how that's different than what we saw in the vertical trend. In the vertical trend over on the left, we saw the 3s and the 4s different energy levels. But here, 2p versus 2p, we're in the same energy level. Same energy level, same orbital. So there's got to be something else going on that we can use to explain this. And what we're going to use to explain this is the idea of effective charge from the nucleus. Sometimes you hear this as effective nuclear charge. Because remember, there's two things that's going to impact what's going on with the electrons. The attraction between the nucleus and the electrons, that's certainly important. But also, we can't get all of the electrons really close to the nucleus because, well, they're going to start repelling each other. So let's kind of have a look and see what happens for this horizontal trend. Protons are acting together, pulling on each individual electron, Meanwhile, the electrons are acting separately. So one thing we have to look at here is, being we're in the same energy level, we have to look at what's going on with the protons. In carbon, we only have 6 protons pulling on the electrons. In fluorine, we have 9. Being we have fewer protons in carbon, they're not able to pull the electrons in as close, and we end up with a bigger size. For fluorine over here on the right, what we're looking at is we have 9 protons. That's going to have a very strong pull on each electron in there, bringing it very, very close to that nucleus. What we don't want to do is we don't want to think about it, well, 6 protons, 6 electrons, 9 protons versus 9 electrons. That's not the way we want to look at it. It's not a 1-to-1 ratio that matters. What you really have to look at is the protons acting together in unison, the electrons acting separately. So the real analysis with this is each electron in carbon is getting pulled in by 6 protons in carbon. But for fluorine, each electron is being pulled in by 9. Those 9 protons in fluorine can pull the electrons in closer. So carbon has fewer protons pulling on the electrons. It cannot pull them in as close. Fluorine has more protons, allowing it to pull the electrons in closer. So that's why we see, as we increase the number of protons, as long as we are in the same energy level, we're going to get smaller. And that's why your size is decreasing as you move to the right across the periodic table. The next trend we want to look at is ionization energy. And for this one, we want to actually have a little definition for ionization energy. So when we're looking at ionization energy is the amount of energy required to remove an electron from an atom in the gas state. We have to look at this in the gas state because what we really care about is what's happening within one atom. When we look at a gas particles are separated. Atoms in the gas phase are far apart. Here we can look at what's happening internally within an atom. If we were looking at a liquid or a solid, we'd have multiple different things we would have to deal with. We'd be looking at not only what happens within an atom, but we'd be looking at what happens between different atoms. And that would very much complicate the picture. We want to look at what's happening internally, what's happening within one atom. To do that, we have to be in the gas phase. If we go into the liquid or the solid, the atoms are so close, we have other effects that can be happening. It's really important that we understand what happens with the size trend, because we're going to use the size trend to deal with what's happening with the actual ionization energy. Ionization energy follows inversely with what's happening with size. So ionization energy will decrease as you move down the periodic table and increase as you move to the right. So let's think about what that means. The smaller the atom is, the closer the electrons are to the nucleus, the more tightly held they're going to be, requiring more energy to remove it. So the closer an electron is to the nucleus, the more tightly held it is to that nucleus. That's going to mean more energy in order to successfully remove it. If an electron is very far away from the nucleus, it's not going to be feeling the full pull from the nucleus. It's going to be held more loosely. If it ends up being held more loosely, it's not going to take as much effort, as much energy in order to remove it. So ionization energy is following the opposite of what's happening with the size trend. Now I want to give you a non-chemistry example to kind of think about what's happening in this relationship to size and ionization energy. This one's going to be a money example. I want you to think about going out to a very crowded outdoor event in winter. Maybe think about Times Square on New Year's Eve. there's a whole bunch of people. Anytime you have a whole bunch of people, it attracts thieves. It attracts pickpockets. I want you to think on a cold winter day when you're out in public in a place that has a lot of people, where would you want to put your money in order for it not to be stolen? Well, the best place to put it would not be if you're wearing layers because it's going to be cold, in that outermost jacket pocket. That would be very easy for a pickpocket to come in and remove that. A thief could steal that very easily because you wouldn't feel it. Your body isn't really feeling that wallet. That wallet is so far away from your body, it would not take much effort for a thief to come in and steal that. Very easy. That would be a low ionization energy if this were an electron. But now, let's put this a different way. Now, let's imagine we're wearing layers. We decide to put our wallet or our purse or our billfold on an inner jacket pocket. We have multiple layers over that. In that pocket is very, very close to our bodies. If it's that close to our bodies, it's going to be really hard for a thief to come in and steal it. It would take a lot of effort or extraordinary skill in order to do that. You'd be looking at someone like David Blaine, street magician, in order to come in and steal that away. Put that back in terms of the electron. Electron close to the nucleus, high ionization energy. A lot of work needed in order to remove it. So far away from the nucleus, low ionization energy. Close to the nucleus, very high ionization energy. You see that inverse relationship between size and ionization energy. And that really helps you kind of follow one trend from the other. Think about where you're going to put your wallet. Your wallet is the electron. Your body is the nucleus. The closer you put your money to your person, your actual body, the harder it is for somebody to steal. We can talk not only about losing one electron, we can talk about losing multiple electrons. So what I did is I put some data here for aluminum. So I listed the first, the second, the third, the fourth, the fifth, and the sixth ionization energies. And I have these listed in kilojoules per mole. The first, 580 kilojoules. The second, 1820. The third, 2,740. The fourth, over 11,000. The fifth, 14,000. And finally, the sixth, 18,000. Now, there's a couple things you want to notice right away about this data. First thing you want to notice is it's increasing. On each step that we go to, we have an increase. 580, 1820, increase. 1820 to 2740, increase. 2740 to 11,600, increase. 11,000 to 14,000, increase. 14,000 to 18,000, we're seeing an increase again. So each electron we're trying to remove is getting successively harder, more ionization energy, more difficult to remove. And this should make sense because remember, what's going to dictate that closeness to the nucleus? Well, it's going to be that pull from the nucleus, but it's also going to be electron-electron repulsion. Every time we remove an electron from the atom, we're going to reduce electron-electron repulsion. As we do that, what's left is going to get smaller. Fewer electrons means they can get a little bit closer to the nucleus. So I'm getting a little bit closer to the nucleus with all the electrons. Remove another one, less electron repulsion, and get a little bit closer to the nucleus. Closer to the nucleus. Closer to the nucleus, because now I don't have as many electrons fighting for that spot. Electrons are going to repel each other. The fewer electrons I have, the closer the rest can get to the nucleus. So that's the first thing you want to see, is it's always an increasing in ionization energy. Each electron that we remove allows the other one to get closer, and that's why we're seeing an increase. There's another thing we want to look at with this data. And the other thing we want to look at with this data is just looking through these numbers, there's another thing you can really see in this data. Besides the fact that they're all increasing, we already talked about that, what you will also see is a big jump. So between the third and the fourth, we're seeing a gigantic jump in the ionization energy. 580 to 1820, bigger, but not a huge increase. 1820 to 2740, bigger, but not a huge increase. Here's this big increase, 2740 to 11,600. That's a huge increase that doesn't follow with the rest of them. Yeah, I have some okay to moderate size increases, but I'm looking at this one really big increase between the third and the fourth ionization energies. That's going to tell a really important story. So I want to tell us, or we want to talk through what that's actually telling us with this. Now we're looking at the right-hand part of this slide. And here we're actually going through the process of what's happening along with the electron configuration. So this 580, what does that refer to? Well, that's referring to aluminum losing an electron. That costs 580. Well, the electron it's going to lose is the one that's farthest away from the nucleus. So it's written in red, but I'm also circling it here. That electron lived in a 3p orbital. So to remove that electron costs 580. And that was the first ionization energy. Now if I go to the second, this says 1820. Well, what's the second ionization energy mean? I already lost one electron, so I'm going to start with aluminum plus 1. Now I'm going to lose another electron. Well, what electron am I losing? Well, the electron I'm losing now, is one highlighted in red, circling also in purple, comes from a 3s orbital. That costs 1820. Now when I go to the third ionization energy, 2740, this is how much it costs to remove that third electron. So I already lost 2, so I'm starting at aluminum plus 2. To lose the third one, I go to aluminum plus 3. What electron am I losing? The electron I'm losing is in this 3s orbital again. That costs 2740. Now as I go to the fourth ionization energy, I'm trying to lose that fourth electron. I'm going from aluminum plus 3 to aluminum plus 4. Look now at the electron we're going to remove. The electron we're going to remove now comes from a 2p orbital. And look at how much more that costs. Before, we kind of go back and look at what orbitals were, which electrons were we removing? Well, 3p, 3s, 3s, now 2p. The energy level changed here. Being the energy level changed, now I'm in the second energy level. You compare where an electron's at in the second energy level to the third energy level, an electron in the second energy level is much, much, much closer to the nucleus. If it's much, much, much closer to the nucleus, it's going to be a lot harder to remove that, and we see that big jump. If we go on to the fifth and the sixth, we still see it's increasing, but I don't see that same huge jump that I saw before, because now if I'm highlighting which electrons we're moving, the fifth electron we removed, still from that 2p, and the sixth electron, still from that 2p orbital. So that big jump matched onto us changing from what electron we were removing and what energy level was it at. 3s didn't cost us much, 2740. 2p, 11,600. And that's going to be a key thing that we're going to look at. Ionization energies can tell you something critical about the element that you're dealing with. I want to show that to you in the next slide. Next slide, we want to talk about something called valence electrons. These valence electrons are those electrons in the highest energy level in an atom. We care more about these than the other ones because these are the electrons that are most important when we're talking about chemical bonding. These are the electrons that are involved. It's not going to be the electrons close to the nucleus, it's going to be those farthest out. So what I did is I rewrote out the electron configuration for aluminum. 1s2, 2s2, 2p6, 3s2, 3p1. The highest energy level I have is the third energy level. If I count how many electrons I have in that third energy level, I have 2 that live in the s and 1 that lives in the p. That's going to give me a total of 3 valence electrons. If I do this for some different elements, if I do the same thing for fluorine, fluorine's 1s2, 2s2, 2p5, the highest energy level is the second energy level. Well, if I look at how many electrons are in that highest energy level, 2 are in the s, 5 are in the p, that's going to give me my total of 7 valence electrons I'm looking at. For rubidium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. The highest energy level I'm looking at is 5. How many electrons are in that energy level? Just the 1 there for the 1 valence electron. So you can do this with any element out there, but you don't really need to. You don't need to write out electron configurations to determine the number of valence electrons. Instead, what's much easier is we can just use the periodic table. Earlier in the semester, when we talked about the group numberings for the different chemical groups, we said everyone still used the old numbering system. And now we're finally able to see why everyone uses this old numbering system as well, because the old numbering system is actually better. It tells you some real useful information right away. If you take aluminum and look it up on the periodic table, it's in group 3. Well, how many valence electrons did we say aluminum had? 3 valence electrons. Fluorine. If you look at fluorine on the periodic table, it's in group 7. How many valence electrons are we looking at there? 7 valence electrons. Rubidium, find that on the periodic table, that's in group 1A. How many valence electrons? Well, that's just going to be 1. That's why everyone still uses this older numbering system on the periodic table. It's telling you right away how many valence electrons you're looking at. Anything in group 3A is going to have 3 valence electrons. 7A, 7 valence electrons. You're looking at something in group 1A, 1 valence electron. Even those things that are not listed in here, group 2A would have 2 valence electrons. Group 4A would have 4 valence electrons. 5A, 5 valence electrons. 6A, 6 valence electrons. It's that easiness and that information that's readily out there is why everyone is still using this older group numbering system. It gives you the valence electrons right away for that element without even having to write out electron configurations. What I want to do is I want to pair up this idea of valence electrons with what we just did with multiple ionization energy. So I want to show this slide that we saw right away from before, even before we saw valence electrons. Whenever you see this big jump, remember, here's where the big jump happened between 3 and 4. That big jump between 3 and 4 told us how many valence electrons. 3 valence electrons, because those 3 were relatively easy. They were in the outermost energy level. Once we tried to remove a 4th, it got really hard. So even if we didn't know this was aluminum, let's pretend this one, you didn't know that this was aluminum, and you just had this ionization energy information. Imagine that's the only thing you have. Now, you may not be able to determine specifically that it's aluminum, but you would be able to determine that you would definitely be looking at something in group 3A. You knew it would have to be in group 3A because of the big jump. The big jump between the third and the fourth told you it was going to be having 3 valence electrons, meaning it's going to come from group 3A. Now you might be able to do a little bit more. You might be able to eliminate something from this. I mean, let's think about some other options. You could probably eliminate boron from this. Boron only has 5 electrons. Well, I got 6 ionization energies here, so we knew it wouldn't be boron, so we could eliminate that from the list of possibilities. But we wouldn't know necessarily that it was aluminum, but you would know for certain you were looking at something in group 3A. And this is how you could use ionization energy to potentially narrow down or identify an unknown element. You would look for the big jump in ionization energies. Here that big jump was between third and the fourth ionization energy. That's telling you, hey, this has 3 valence electrons. I need to be looking in group 3A. If that big jump happened between the first and the second ionization energies, well, that's going to tell you, hey, that's going to be in group 1A. If it's between the second and the third, if that's where the big jump happens, well, then that tells you, hey, I'm looking at 2 valence electrons. I should be looking at group 2A. We saw what happens when the big jump comes between the third and the fourth. You get 3 valence electrons, group 3A. If the big jump would happen between the fourth and the fifth, what that's telling you is that you would have 4 valence electrons. You'd be looking at something in group 4A. The big jump comes between the 5th and the 6th ionization energies. That information then is telling you have 5 valence electrons. Group 5A. Something between the 6th and the 7th. Well, that's going to be telling you that you have 6 valence electrons. Look in group 6A. You can go on and on with this. That big jump tells you how many valence electrons you are actually dealing with, and you can identify elements by using that, or at least know with high level of certainty. And if you can't identify the specific element, you could at the very least know what group you would be looking at for these.